Every day, you type an easy-to-remember name, like www.google.com.
The magic is that computers only communicate using complex strings of numbers, known as IP addresses. So how does the internet instantly translate the name you typed into the correct numerical string to find the server? The answer lies in the DNS, the internet's massive, decentralized, and global phone book.
This entire complex process happens continuously in mere milliseconds. Without it, the whole internet would instantly collapse.
This video will demystify DNS, from the root servers to the protocols that help you access every single website.
The core problem is simple. Humans easily remember names, but computers only understand and use numerical IP addresses.
You certainly can't remember a series of numbers like 172.217.44.78 for every website you want to visit daily.
DNS is the global translation system, automatically converting a domain name into its corresponding numerical IP address.
DNS is intentionally designed as a complex hierarchical system without a single central server that could fail. This decentralization ensures that no single point can crash, maintaining the stability of the entire global network. When you type an address, your DNS request must pass through 4 different types of servers to find the final answer.
These 4 servers are the recursive resolver, the root server, the TLD server, and the authoritative server. The recursive resolver, usually your ISP's server, is the first and most crucial stop for the query. It accepts the request from your browser and commits to finding the final, definitive answer at all costs.
The root server is the highest point in the DNS hierarchy, marking the definitive starting point for every query.
There are only 13 specific IP addresses for the root servers, but they are replicated into hundreds of servers worldwide.
The TLD server, top-level domain, manages the high-level extensions, like .com.
The authoritative server is the final and most important server, as it stores the exact IP address of that specific website. When you type exampledomain.com, your browser sends the first request to the recursive resolver copy.
The recursive resolver begins the search by asking the root server, what is the IP address for exampledomain.com? The root server doesn't know the answer, but it knows which server manages the .com domain, the TLD server.
The root server replies, "Go ask the .com TLD server."
The recursive resolver continues by sending the same question to the designated .com TLD server address.
The .com TLD server replies, "I don't know the IP, but ask the authoritative server for example domain."
Finally, the recursive resolver sends the last query directly to the website's authoritative server. The authoritative server replies with the precise IP address, for example, 104.20.12.33.
The recursive resolver then sends this verified IP address back to your browser, and the website begins to load instantly. This complex, multi-step process typically happens in just a few milliseconds, so quickly you never even sense the delay. Without caching, this entire 7-step procedure would have to repeat for every single web request you make.
The recursive resolver stores the verified record's IPs it has found in its memory for a specific amount of time.
This storage duration is set by the TTL, time to live, value, established by the website owner.
If you revisit that website within the set TTL window, the query is answered instantly from the cache.
TTL ensures a vital balance between fast access and timely updates when the website's IP address needs to change. Caching doesn't just happen at the ISP, it also takes place locally on your browser and operating system.
DNS stores more than just IP addresses. It maintains various different record types for specialized purposes.
The most crucial record is the A address record, which maps a domain name directly to an IPv4 address. The PO-A record performs the identical function, but is specifically used for the longer IPv6 addresses.
The CNAME canonical name record creates an alias, pointing one domain name to another existing domain name. The MX record specifies which specific server is responsible for receiving email for that domain.
The TXT record is commonly used to store verification text data for security and ownership purposes. Security is a major concern for DNS, as it is a prime target for high-level phishing and hacking attacks. DNS spoofing is when an attacker provides a false IP address, maliciously redirecting you to a fake website.
DNSSEC, Domain Name System Security Extensions, is an essential security layer that uses digital signatures. DNSSEC ensures that the DNS data you receive is authenticated, correct, and has not been tampered with in transit.
The future of DNS is quickly shifting towards DNS over HTTPS and DNS over TLS protocols. These protocols encrypt DNS queries, hiding them completely from your ISP and other potential middlemen. This critically protects your online privacy, preventing the tracking of your web history through DNS queries. DNS is essential technology for the deployment of global content delivery networks news.
CDNs use DNS records to intelligently route users to the nearest geographical edge server to maximize loading speed. This is precisely why massive websites like Netflix and Amazon can load instantly anywhere in the world.
The DNS system must constantly cope with massive-scale distributed denial-of-service attacks. Attackers attempt to overwhelm the DNS servers, preventing them from answering legitimate user queries.
Modern DNS services use enormous traffic filtering and load distribution systems to effectively mitigate these attacks. The use of DNS for load balancing allows a single domain name to be mapped to multiple server IP addresses. This distributes incoming traffic across a group of servers, ensuring no single server becomes overwhelmed or fails. When one server fails, DNS can automatically and instantly stop routing traffic to the address of that failed machine. SRV records are used to locate various network services like VoIP or online gaming servers. They help client devices automatically find and connect to specific service servers without needing to know their direct IP.
The DNS management system allows network administrators to update their records and changes to take effect within minutes.
A process of changing a website's IP address will cause zero disruption if the TTL value is configured optimally.
DNS is an open standard, managed by multiple independent organizations, ensuring global stability and interoperability.
This decentralization contrasts sharply with proprietary network systems, which are prone to single points of failure or manipulation.
The future shift is toward edge DNS, where solution nodes are located closer to the...
This dramatically reduces latency, boosting the speed of domain name resolution and improving the overall user experience. The domain resolution process is a continuous, complex computational feat, happening trillions of times every day globally.
Though often invisible, DNS is one of the most critical systems by scale and importance to the entire internet.
The stability of DNS is the fundamental backbone for the global financial network, mobile communication, and every online app. Without DNS, you would be forced to access every website using a number string, making the internet virtually unusable. DNS is the architectural genius that made the internet friendly, intuitive, and highly accessible to billions of global users. It is a highly intelligent distribution system, meticulously ensuring that a local fault cannot crash the entire global network. It represents the pinnacle of network engineering, combining decentralization, caching, and security for robust operation. Finding a web page is only the first step. DNS continues to manage your data flow across the entire network infrastructure, What everyday service would instantly collapse without the continuous operation of the DNS system? Share your thoughts.